Solar wind sputtering adds a far more variable, often dramatic contribution on top of that steady baseline, concentrated primarily in the regions where Mercury's weak and lopsided magnetic field allows solar wind particles to funnel directly down to the surface, mainly near the poles and in specific cusp regions, and intensifying sharply and rapidly during solar storms and coronal mass ejections. Micrometeorite bombardment provides a constant background contribution across all detected elements, but emerges as the dominant, most efficient source, specifically for heavier elements like calcium and magnesium, and produces dramatic, predictable spikes during Mercury's regular encounters with cometary debris streams, such as the one associated with Comet Encke. Thermal effects play a smaller, more supporting role in the overall system, particularly influencing how quickly atoms redistribute themselves once airborne, since Mercury's extreme day-night temperature swing significantly affects how individual atoms bounce, temporarily stick, and eventually re-release from the surface as the planet slowly rotates beneath the unforgiving glare of the sun. In other words, Mercury is not leaking metal atoms for one simple, isolated reason. It is leaking metal atoms because it exists in an environment of truly constant bombardment, from raw sunlight, from the ever-present solar wind, and from streams of ancient space debris, and its varied surface chemistry responds differently to each distinct kind of assault, releasing different elements through different physical processes, all happening simultaneously, all the time, across the entire planet. At this point, you might reasonably be wondering, fine, this is a genuinely fascinating chemistry and physics puzzle, but why should anyone outside a fairly small circle of planetary scientists actually care about the details of how Mercury loses trace amounts of sodium? Here is why this discovery genuinely matters, well beyond Mercury itself. Mercury belongs to a broad category of worlds scientists refer to as airless bodies, a category that includes our own moon, many of the larger asteroids scattered through Ut, the solar system, and countless moons orbiting the outer planets from Jupiter's ice-covered Europa to Saturn's cratered Rhea. Every single one of these worlds shares the same fundamental challenge that Mercury faces. Essentially, no meaningful atmosphere to speak of, constant direct exposure to the solar wind and micrometeor, high bombardment, and exposed surfaces made of raw rock, dust, or ice, with nothing standing between them and the harsh space environment. Understanding, in precise detail, exactly how Mercury simultaneously loses and continuously regenerates IT's thin exosphere gives scientists an invaluable working model, essentially a natural laboratory, for understanding surface-atmosphere interactions across dozens of other airless worlds that are far more difficult, expensive, or currently impossible to study up close. This research also matters for something surprisingly close to home. Our own moon possesses its own extremely faint exosphere, and for years, scientists genuinely debated exactly how much of it originates from solar wind sputtering versus micrometeorite impacts versus other competing processes. The newly refined multi-process understanding developed through decades of Mercury research is now being actively applied to reinterpret older lunar exosphere data collected by previous missions, and is directly informing the design of new instruments intended for future moon missions, including NASA's ongoing Artemis program, which aims to place detailed, sensitive exosphere monitoring instruments on the lunar surface for the first time in the modern era of space exploration. There's also a deeper, almost philosophical dimension buried within this discovery. Mercury's surface is very slowly, continuously eroding, not through wind or rain, since the planet genuinely has neither, but through this relentless atom-by-atom stripping process, driven directly by the very same sun that Mercury orbits so intimately close to. Every single day, without pause, sunlight, solar wind particles, and drifting cosmic dust are gradually, invisibly sandblasting Mercury's surface at the atomic level, flinging trace amounts of the planet itself outward into space, where the overwhelming majority of those individual atoms are lost forever, and only a small fraction settle briefly into the faint, comet-like tail that Mercury quietly drags along behind it as it races around the sun. Mercury has been undergoing this slow transformation for well over 4 billion years, since the earliest days of the solar system. It will almost certainly continue doing so for billions of years still to come. A slow, silent, continuous transformation. It's entirely invisible to the unaided human eye, only recently made visible to us at all through spacecraft instruments sensitive enough to detect the faint glow of individual atoms scattered by sunlight all the way from 91 million kilometers away. The story is far from finished. Bepi Colombo, the ambitious joint mission between the European Space Agency and the Japan Aerospace Exploration Agency, is continuing to gather fresh data as it settles into its final dedicated science orbit R, on Mercury. Unlike Messenger, which relied on a single orbiter, Bepi Colombo carries two entirely separate spacecraft working in tandem, each equipped with complementary scientific instruments, allowing researchers to study Mercury's exosphere ray and its surrounding magnetic environment simultaneously from two distinct vantage points at once, a capability that was simply never possible during any previous mission to the planet. Early data returned from Bepi Colombo is already helping to refine this picture even further, delivering more precise measurements of exactly how much sodium, calcium, and magnesium departs the surface under a wide range of differing solar conditions, and helping scientists construct increasingly accurate predictive models capable of forecasting, almost like a genuine space weather report, how Mercury's faint, drifting tail of escaping metal atoms is likely to change from week to week, depending directly on real-time solar activity. Scientists are also hopeful that these ongoing findings will eventually help illuminate Mercury's deep geological past, because different minerals release their constituent elements through distinctly different processes and at different rates. The precise chemical composition of Mercury's exosphere can function almost like a rolling fingerprint of the planet's underlying surface geology over time, potentially helping researchers eventually map out where sodium-rich or calcium-rich rock formations are concentrated across regions of Mercury that spacecraft cameras still haven't been able to observe in truly high resolution. So the next time you happen to glimpse Mercury, a small, steady point of light hanging low on the horizon, not long after sunset, easy to miss if you're not specifically looking for it, remember that this small, unassuming little planet is, at that very moment, quietly leaking itself into the vacuum of space, one atom at a t. I.me., sandblasted continuously by raw sunlight, battered periodically by gusts of solar wind, and peppered on a predictable schedule by streams of ancient comet dust, in a slow and elegant process that took humanity fully 50 years of dedicated spacecraft exploration, from that first Mariner 10 flyby in March of 1974 to the ongoing work of Bepi Colombo today, to finally properly understand. And right now, at this very moment, trillions upon trillions of individual sodium atoms are streaming continuously off Mercury's surface, forming a faint, invisible tail stretching for millions of kilometers behind the planet as it races around the sun, a comet's tail trailing behind a world that is most certainly not a comet, and one of the strangest, most delicate, and most beautiful side effects of simply existing this close to a star. White Island is what geologists call a stratovolcano, the classic steep-sided cone shape, built up over thousands of years from layers of lava and ash. But the 2019 eruption was not a full magmatic event. Scientists believe it was most likely a phreatic eruption, a steam eruption. Here is how that works. Stratovolcanoes are riddled with cracks and fissures, water seeps. Those cracks from rainfall, from groundwater, from any available source. When that water travels deep enough to encounter the intense heat of the magma below, it flashes instantly into superheated steam. Under normal conditions, that steam escapes slowly and steadily through vents in the volcano's surface, those plumes of white vapor that make White Island look so dramatic in photographs. But at times those vents become blocked. Pressure builds with nowhere to go. When the pressure exceeds what the rock above can contain, it explodes, blasting steam, superheated gas, ash, and rock fragments outward with tremendous force. Steam eruptions are considered relatively small on the volcanic scale. They do not produce massive lava flows or towering ash columns, but at close range, they are absolutely lethal. Superheated gas alone can cause catastrophic burns to exposed skin and lungs within seconds of contact. And the most dangerous characteristic of steam eruptions is their unpredictability. They can strike with almost no warning. No precursor earthquakes large enough to detect in real time. No dramatic surface changes, no visible buildup, just ordinary volcanic activity, and then an explosion that kills everyone nearby. That is why, even with level 2 alerts in place and monitoring systems watching the volcano, no one could predict the exact moment White Island would erupt on that clear blue afternoon. The science was correct. The warning was real. But the nature of steam eruptions meant that the specific timing was invisible right up until the moment it happened. That distinction between knowing a volcano is dangerous and knowing exactly when it will act is at the heart of every volcanic disaster in history. Around the world right now, volcanoes are showing signs of unrest, some quietly, some dramatically. Scientists are not asking whether the next major eruption will happen. They are asking when, where, and how prepared we will be when it does. West of Naples, Italy, there is a place that most tourists walk through without ever realizing what it is. There is no mountain, no cone, no dramatic peak rising above the skyline. Instead, there are towns, ports, roads, neighborhoods, people going about their daily lives in complete comfort. What they are living on top of is one of the most dangerous volcanic systems in Europe, a supervolcano called Campi Flegrei, which translates as burning fields. Unlike a traditional volcano, that builds upward over time, a supervolcano blows downward, leaving behind a massive bowl-shaped depression in the earth called a caldera. Campiflegre's caldera is so enormous that you could stand at its center and never realize you were inside a volcanic system. A significant portion of Naples itself is built directly within it. Homes, schools, roads, and businesses, all sitting on ground that is still geologically active. The caldera breathes. Scientists call the phenomenon Brady schism. The ground rises and falls slowly over time as pressure builds and releases underground. Entire neighborhoods have shifted up or down by feet across the centuries. There is physical proof of this sitting. In the town of Pozzuoli, an ancient Roman structure called the Temple of Serapis, whose stone columns are marked with holes bored by marine organisms that only survive underwater. Those holes tell geologists that, at some point in history, those columns sank below sea level and stayed there for a long period before they grow. And rose again. The earth moved, slowly, over centuries, and it is moving again now, faster than it has in decades. Since April 2025, the ground in the Campiflegre region has been rising by approximately 6 inches every single month. In geological terms, that is rapid movement. Buildings are not engineered to shift like that. Foundations crack, pipes stretch and burst, roads buckle, and all of this is happening while an underlying ring fault system is being pulled tighter and tighter by the accumulating pressure below. Scientists applied machine learning to analyze more than 54,000 recorded earthquakes in the Campiflegre region. When visualized, the data looked like chaos, thousands of scattered points with no discernible pattern. But when artificial intelligence processed the entire data set at once, this only thing emerged from the noise that had never been clearly identified before. A large circular fault system, ring-shaped, outlining the edge of the caldera, became visible. It had always been there. It was buried in the complexity of the data, invisible to manual analysis. Once identified, it fundamentally changed how scientists understand the pressure dynamics of the entire system. A ring fault acts as a pathway. Instead of pressure dissipating evenly through solid rock, it concentrates along the ring and moves more efficiently toward points of weakness. And the research identified the weakest point in the system, directly beneath the densely populated town of Pozzuoli. Magnitude 5 earthquakes are not just possible there. Scientists say they are likely. And these are not deep earthquakes that produce slow, rolling motion. They are extremely shallow, sometimes originating just a few thousand feet below the pavement. The shaking is vertical, violent, and amplified by the proximity to the surface. A magnitude 5 shallow earthquake here hits with the intensity of a truck crash directly beneath your feet. And the buildings throughout this region, many of them centuries old, built with thick stone walls long before modern seismic engineering existed, are not designed to handle that kind of force at all. If conditions escalate toward a major eruption, the evacuation challenge would be one of the most complex logistical operations in modern European history. The red zone directly around Campiflegre holds approximately 500,000 people. The adjacent yellow zone adds another 800,000. The streets in these areas are ancient, narrow, winding, built for cart and foot traffic, not for mass vehicle evacuation. Getting that many people out simultaneously through that road network is not a plan that can be improvised on the day. Right now, schools in the Campiflegre area remain closed as a PR, a cautionary measure. The Italian government has committed more than 500 million euros towards structural reinforcement and safety upgrades in the region. A yellow alert remains active. Scientists are watching every reading closely, and the concern in the research community is real and growing. Across the Pacific, a very different kind of volcanic story is unfolding. 300 miles off the coast of Oregon, nearly a mile beneath the surface of the ocean, a volcano is preparing to erupt. Scientists are not speculating. They are confident, and they are getting ready to docky. You meant it in real time. Axial Seamount is the most active volcano in the Pacific Northwest, almost entirely unknown to the general public because it sits completely underwater. It is nearly 3 times taller than the Empire State Building measured from its base on the ocean floor. It has been under continuous scientific surveillance since the 1990s, when researchers installed a permanent network of seafloor instruments that now relay real-time seismic, thermal, and deformation data directly to labs on shore. It hosts the world's first permanent underwater volcanic observatory. And by mid-2024, it had inflated the seafloor above it, rising measurably as magma accumulated in the chamber below, to levels nearly identical to where it was just before its last eruption in 2015. The pattern is clear. The timing fits. An eruption is expected, BEFO, early 2026. The good news for anyone living on the coast is straightforward. The water pressure at that depth prevents explosive surface activity. There will be no tsunami, no ash cloud, no danger to people above the surface. What will happen is a flow of lava across the seafloor, spreading across miles of ocean bottom. Dramatic in geological terms, harmless to humans. But for the scientific community, this eruption is an extraordinary opportunity. For the first time ever, a major underwater volcanic eruption will be observed and recorded in real time. Rough fiber optic cables connecting seafloor instruments directly to shore. Every pressure reading, every seismic tremor, every temperature change, captured live. The data will not just advance understanding of axial seamount, it will improve the tools scientists use to predict eruptions at volcanoes on land, the ones that directly threaten human lives. Beyond individual volcanoes, there's a larger and more uncomfortable conversation happening in the scientific community. The world is not prepared for a supervolcano eruption. Researchers analyzing ice cores from Greenland and Antarctica, natural archives of the Earth's atmospheric history stretching back hundreds of thousands of years, have found evidence of multiple past eruptions that dwarfed anything in recorded history. Based on that historical record, scientists calculate a real and statistically significant probability of an eruption occurring within the next century that is 10 to 100 times more powerful than the 2022 Hunga Tonga Hunga Ha'apai event, a 1 in 6 chance. The last eruption of comparable magnitude was Mount Tambora in Indonesia in 1815, the most powerful eruption in recorded man history. It killed tens of thousands of people directly. The ash and sulfur dioxide it sent into the upper atmosphere blocked enough sunlight to drop global temperatures by approximately 1 degree Fahrenheit. The following year became known as the year without a summer. Crops failed across Europe, North America, and Asia simultaneously. Famine spread. Disease followed famine. The economic and humanitarian consequences rippled across the globe for years. Tens of thousands more died from the indirect effects than from the eruption itself. That was in a world of 1 billion people with limited global trade dependencies. Today, 8 billion people depend on interconnected food supply chains that have almost no buffer. A major volcanic cooling event in the modern world would not just reduce crop yields in a few countries, it would trigger cascading failures acro, ESSA systems that have been optimized for efficiency rather than resilience. Food prices would spike globally within months. Supply chains would fracture. Nations dependent on agricultural exports would face economic collapse. The political consequences would be severe and unpredictable. Volcanologist Michael Cassidy from University of Birmingham, has framed the disparity plainly. Space agencies spend billions every year on planetary defense against asteroid impacts. The probability of a supervolcanic eruption causing comparable or greater civilizational damage is meaningfully higher than the probability of a civilization-ending asteroid strike. And yet, there is no global plan for a supervolcanic response, no international coordination framework, no agreed food reserves against volcanic cooling, no coordinated evacuation protocols for the highest risk zones, nothing approaching the level of preparation that the risk actually warrants. Climate change is adding further complexity. As glaciers melt in Iceland, Chile, and Indonesia, 3 of the highest risk volcanic zones on Earth, the pressure those ice sheets exert on underground magma systems decreases, making eruptions more likely. Increased rainfall, another consequence of warming, is directly relevant. To phreatic eruptions of the type that occurred at White Island. Water seeping into volcanic fissures under greater pressure and in greater volumes increases the probability of steam-driven explosions. The intersection of climate change and volcanic risk is not a distant scenario. It is active right now, and scientists are mapping it with urgency. The story that began with White Island on December 9th, 2019, is really a story about warnings. Scientists raised the alert a month before the eruption. The data was clear. The sulfur dioxide readings were elevated. The alert level was official. And the response was to keep sending tourists into the crater because it had always been fine at level 2 before, until it was not. That pattern, science issuing warnings, institutions slow to respond, repeats itself across the global volcanic landscape. Campi Flegrei has been showing signs of accelerating unrest for years, and 500,000 people still live in the red zone. Axial seamount is about to erupt. And the opportunity it represents for better prediction tools is only valuable if those tools are then funded, developed, and applied to the volcanoes that actually threaten populated areas. And at the planetary scale, the warnings from ice core data and volcanic history are clear, while the global preparation remains essentially non-existent. Volcanoes do not negotiate. They do not wait for convenient timing. They do not consider economic calendars or evacuation logistics or the fact that 47 tourists are walking near the crater on a clear, perfect afternoon. At 2:11 p.m. on December 9th, 2019, White Island delivered that message in the most devastating way possible. Scientists had warned us. The question that the world has not yet answered is what we do with the next warning. Before it becomes another story of what we should have done,